I found it really helpful to think about quantum field theory in particular in terms of data sets and signal analysis. And that's the perspective that I'm going to try to develop through the course of this talk. So I'm going to start with a discussion of quantum mechanics and classical mechanics as dataset formalisms. So really not about ensembles of particles, particle properties at all. After the end of this talk, we can talk about how this might perhaps relate to particle properties, but that's not going to play a part at all. And then I'll talk about classical mechanics and how we can use the Poisson bracket to introduce non-commutativity into classical mechanics in a way they're called CM+. And because we'll be thinking more classically about physics, we'll need to know what the difference is between quantum noise and thermal noise. They clearly can't be the same. And I'll argue that the difference is to be found in Lorentz invariants. So then less about data sets, more about signal analysis. I'll talk about quantum field theory in that sort of way and show you how we can construct within quantum field theory what I'm going to call quantum non-demolition field theory, which is a terminology from quantum information, which effectively is a noisy classical field. And that's derived from an article by Tsang and Caves in 2012, which effectively does this construction for a simple harmonic oscillator, and so fairly naturally it crosses over to quantum field theory. Then I'll introduce renormalization as a motivation for introducing a particular kind of, excuse me, I shouldn't look up there, it just makes me dizzy, for introducing a particular kind of nonlinearity into the Whiteman axioms in particular for quantum field theory, and that will give us a way to introduce a measurement theoretic path towards quantum gravity and quantum non-demolition gravity, as I'll call it. But I'm going to start with an elementary, concrete matrix model, where if we have a data set M, for which the data values are just M1, M2, and so on, and you have associated with those relative frequencies, P1, P2, and so on, and if those are actual relative frequencies, then they'll be rational numbers. If they're expected relative frequencies, then they'll be real numbers. We'll allow them to be real numbers. Because we can, yeah, go on. Actually measurement? I mean, you've got a data set on your computer. And that, in a sense, is the data that you have available to you. So we're starting from the data instead of starting from the theory, is the kind of aspect we're doing here. We kind of sidestep the measurement problem by doing this, but of course, it's in the, as things go along, we'll see how I think we really do sidestep the measurement problem by taking this approach.
And really has to be rational resolution.
No, just because if you have a data set of, say, 100,000 entries and you have 17 of those are a particular value, then it's going to be 17 divided by 100,000 is going to be the relative frequency. It's going to be rational. Right. Yeah? No. So we can write this just as the trace of a product of matrices with the M1 values down the diagonal of a particular base in a particular basis, and that will pick out a particular set of values down the density matrix, a density operator as may be, and a measurement operator. And so in terms of quantum mechanics, we'd of course call this a density operator, and we'd expect these properties, which would ensure that these are right for them to be relative frequencies. So now for a different data set, though, where we have a matrix representation of a different operator that's diagonal in a different basis. So consequently, in that different basis, the density operator will have a different set of values down the diagonal. So that will give us pi prime, where we would have pi if it was in the same basis. So what we've done here is we've encoded into a single formal structure multiple probability spaces. It's just mathematics. There's no physics in this at all. There's definitely no H bar. This is just what a mathematician would call a generalized probability theory, a matrix model of generalized probability theory. Now, for traditional classical physics, we would use different initial conditions for different contexts. So you'd have, for a particular initial condition, you'd evolve it forwards and backwards in time using a differential equation. For a different set of initial conditions, you'd evolve it backwards and forwards using exactly the same differential equation. What this formalism gives you, even for classical mechanics, is the ability to put those together and to evolve them backwards and forwards using a unitary evolution, just the same for quantum as for classical as for quantum, as we'll see in a few moments. So from an experiment, we obtain data sets. Those contain lists of numbers. We can construct relative frequencies and other statistics as may be. something in a theory, no matter what the theory is, should generate expected relative frequencies so that we can compare those with the relative frequencies that we actually observe for a data set. Anything more than that doesn't give us better empirical confirmation. But we do want other things. We want ideas such as systems and particle properties, because those can be intuitively helpful. They let us imagine what's happening inside the experiment and guess what new experiment would be nice to have. So those are vital. Nonetheless, in the first instance, the measurements just give us data sets. From those, we have a sort of squiggly line to the particle properties, where sometimes particle properties kind of don't work. Sometimes they work really nicely. When they do, sure, we'll use them. But really, we should be saying we won't have the particle properties in our axioms. We will have the data set property. The data sets themselves will be in the axioms. Clearly, this is a different way of doing things. It's not actually going to make quantum mechanics wrong. It's just a different way of thinking about it. So we derive particle properties. We don't want them in the axioms. There's a sort of quick aside here that data sets really have become the thing in the last 5 to 10 years or 20 years in physics, because machine learning really has a focus on data sets. And this, in some ways, takes that as a guide. Not how I started thinking about this, however. So algebraic classical quantum mechanics and classical mechanics a little bit more formally, not a whole lot. We can begin with a linear operator, and it will correspond to the data values part of a data set. So we have a matrix with M1, M2 down the diagonal. And we do that instead of, as the axioms for quantum mechanics usually do, saying, well, a Hilbert space corresponds to a system, which is considerably further away from the empirical data. So this just takes us closer to the empirical data. I'm going to be very empiricist through all this, but there will be a strong sense of realism by the time we get to the end of the talk, I hope, perhaps. So we have we have these measurement operators. We allow ourselves to add them and multiply them, just as you would. The data set and its data values corresponds to a linear operator and its eigenvalues. We have and that also we can think of in terms of probability theory as a random variable and its outcomes. So now, if the algebra is non-commutative, we'd usually say it's quantum. If it's commutative, we would usually say it's classical. And then we have a bunch of other properties that I'm just going to assume because I want to make contact with Hilbert spaces and operators acting on them. So of course, that doesn't give us any expected data set averages at all. So we introduce, as we did just a few slides ago, a state that tells us for a particular measurement operator what the expected value is, what the expected data set average is. And the nice thing about this formalism is we can just write down the probability distribution for a measurement operator in terms of the direct delta function. This very nicely corresponds to a generating function, to a probability distribution, which we can then use to derive the moments of the probability distribution. And we take the Fourier transform of that, giving us this exponential generating function as well. I'm using the engineer's imaginary here because I actually want to push us towards engineering for the purpose of this talk. You can go back to being physicists afterwards. Now, if you look in the literature, you'll find that state rho maps measurement state rho has to satisfy 4 conditions. It's absolutely standard in literature. They correspond to the rules for relative frequencies, which have to be positive, normalized, and real valued. And correspondingly, we have these 3, which don't look exactly the same, but they actually correspond pretty closely to what we have for relative frequencies. And because we can add relative frequencies, we also have what I call von Neumann linearity, because even if the A and B do not commute, nonetheless, will require this linear condition to be satisfied. Now, this allows us to use measurement operators to modulate the state rho, because this construction here also satisfies the rule for it to be a state as well. And we can have many, many such constructions. And when we do that, this is the basis of what's called the GNS construction, the Gelfand-Naimark-Siegel construction of a Hilbert space. We now have a Hilbert space, the same as we expected in the first place when we were doing quantum mechanics ordinarily, but we've got to it by a slightly different route. But we're still talking about only data sets, not about particle properties. Now, GNS construction also lets us think of a state applied to the vacuum, to a measurement operator. Yes, going around a little, isn't it? Which takes a vector and a covector bracketed around a measurement operator. We can talk of it that way. And the same for a modulated state. So for algebraic classical mechanics, this works out like this. And that is, we ordinarily take classical mechanics to be an algebra of functions on phase space. It has three binary operations: addition, multiplication, and the Poisson bracket. This is completely different from the two binary operations one has in quantum mechanics of addition and composition. But we can construct something much more like quantum mechanics by constructing two classes of operators: multiplication by W, Poisson by W. And for those two classes of operators, we can then use the Jacobi identities in a few lines to derive these non-trivial commutation relations. We have a familiar example here for Poisson by Hamiltonian function, just gives us a generator of time evolution, the Villian operator, which gives us trajectories in phase space and transformations that give those trajectories. And indeed, Poisson by W, we can think of that as W transformations and W trajectories even. So what I've been suggesting for the last few years is that we can use those Z operators as well as the Y operators. That gives us something more powerful than classical mechanics, which is always commutative, and call it Cm plus as a consequence. So long as we're willing to use these Z operators without restriction, and I'll show you in a few slides' time what I mean by that. If we accept that, then that gives us an algebraic measurement theory shared with quantum mechanics, including non-commutativity and all of those things. So we can have, the payoff for this is we can have isomorphisms between Cm plus and quantum mechanics instead of the relationship of quantization.
I've had to insert this fix after the event because of the glitch in the video you've just seen. The payoff for this is we can have isomorphisms between Cm plus and quantum mechanics instead of the much less than isomorphisms between classical mechanics and quantum mechanics that is given to us by quantization and the correspondence principle in the reverse direction. That was all nicely abstract. Now I'm going to specialize to the classical simple harmonic oscillator as an example, but also because it keeps the presentation of a state adequately simple to present it in a talk such as this.
We have, for the simple harmonic oscillator, we have the Poisson bracket is just this antisymmetric form. We have multiplication by Q and by P is straightforward. Poisson by P and Poisson by Q is just a derivative with respect to Q and derivative with respect to P with a minus sign in the second case. And that gives us two copies of the abstract Weyl algebra. We have multiplication by the Hamiltonian function. If that's constant, then that's just the equation for a circle. And then we have the Poisson by the Hamiltonian, which gives us this differential operator. And that generates trajectories, which are circles. So now the natural place to go for a state over this algebra is the Gibbs thermal state for a simple harmonic oscillator at temperature kT, and that's, we will know, is the normal distribution for the simple harmonic oscillator. We can write that using the Dirac delta function in this way, using the YQ and the YP as measurement operators. And that gives us this normal distribution. It's all is working out just the same as quantum mechanics. We can take the Fourier transform of that, which gives us this characteristic function, just Gaussian again. And again, I'm using the engineer's imaginary J. This is now the Weyl-Heisenberg algebra, so it's natural to use the raising and lowering operators, as we do in quantum mechanics. So we can set the multiplication operator to be the sum of a raising and lowering operator, but with KT, where you'd usually expect to see H bar. It's an entirely classical construction. Then the P, the ZP operator becomes just the difference between the raising and lowering operators. And we have for the commutation relations just here and what we expect, what we want from above. And then, of course, we set the lowering operator to annihilate a thermal vector, KT, not a vacuum or a ground state. And then we can use the, well, there's also, we need to introduce B and B dagger for the YP and ZQ. So this gives us, we can use the Baker-Campbell-Hausdorff identity to just derive what the measurement results would be for the ZP and ZQ, although those are anti-Hermitian, so one doesn't want a J. So then we can construct modulated non-equilibrium states just as we do in quantum mechanics, and that gives us a thermal Hilbert space. Completely classical. This could have been done in 1899 if Hilbert spaces had existed then. So now instead of trying to map classical Q and P to quantum Q and P, which doesn't work, we can instead map Q and J partially Q, which we're well used to having the same algebra as Q1 and P1 in quantum mechanics. However, and this is indeed an isomorphism. Same for P and J partially P. However, this is an isomorphism, it's not a unitary equivalence. And so KT is not H bar, is what's going on there. Thermal noise is not the same as quantum noise. We'd like to know what what the difference is between those. There's an immediate sort of thing to look at, and that is that H bar and KT have different dynamic dimensions. So clearly there's a difference there, but it doesn't give us any clue as to what to do next. Where we do get a very strong clue is from quantum field theory, where the quantum vacuum, which is where, so to speak, quantum noise lives, is Lorentz invariant. Whereas thermal noise is very much not invariant under Lorentz boosts. And there's a difference of symmetry properties that can absolutely be used by any classical system. So that's what we'll do. We'll use it in CM+, and then H bar will just be an amplitude of a Lorentz invariant noise, distinct from KT is an amplitude of a less invariant thermal noise. It's a little like the difference between white noise and blue noise, except that this is in terms of wave numbers, not in terms of frequencies. So it's more complicated, inevitably. So from now on, whenever I say CM+, I will mostly mean a field theory. And that's because we can only define the Lorentz group in 1+1 dimensions at the minimum. And of course, we'll want to work in 1+3 dimensions. And we'll also note that for CM+, we have that H bar approaching 0 is no longer a classical approximation. CM+ is perfectly happy with a non-zero H bar. Nonetheless, it's a mean field approximation we'll want to use whenever we can because it will simplify the mathematics. So CM+ can and should include non-commutativity and quantum noise. The measurement theory is just the same as for quantum mechanics because CM+ is just a Hilbert space formalism. And there's a precursor for this. If you don't know about Koopman's introduction of Hilbert space formalism for classical mechanics in 1931, I suggest you go and look it up. It really should be taught, I think, because it makes a contact with quantum mechanics look very different. As I'm trying to persuade you. So there's a more technical difference, however, and that is that for quantum mechanics, the Hamiltonian operator is bounded below, and that has the consequence of analytic properties that are very important in quantum mechanics that we absolutely don't want to lose. Whereas for CM+, if you go the same route, you discover that the Hermitian generative evolution is not bounded below. So it doesn't have those analytic properties. That is a huge difference. It makes enormous difference to the mathematics. But nonetheless, we don't have to use that analyticity. We can choose whether or not we do. We can say, I suggest, that quantum mechanics is an analytic form of CM+. And that's taking the language from signal analysis, where we talk about the analytic signal when there's only positive frequency, whereas we talk about the real signal when it's cosine of omega t plus a constant, which has positive and negative frequencies. So classical mechanics has been strawman for the last 100 years. We are allowed to use partially Q to generate translations. This adjoint action of ZP on multiplication by Q just subtracts a constant. Everyone's happy with that. But we're not allowed to use ZP cubed to generate a unitary transformation in exactly the same way, again, an adjoint action, because that results in the subtraction of a differential operator. That's clearly very different from a traditional classical perspective. But from a quantum mechanical perspective, it's perfectly reasonable. We use ZP cubed to transform just to a different state preparation or to a different initial condition. We can use ZP cubed classically just the same way for classical mechanics, just as we saw for the elementary matrix model on slide number 3. And if we unlock that superpower for classical mechanics, the idea of what an initial condition is becomes more complicated. Just the same as quantum mechanics, you can't just look at one experiment to derive the density matrix. You need to do quite a lot of work. You have to put in lots and lots of what classical mechanics would call different initial conditions. But we know that's worth doing because we use it very productively in quantum mechanics. So we should not, and I wanted to just say quickly that there's more than we said. There are another 10 slides in the appendix, which we're about the measurement problem and about Bell inequalities. But there's no time for that. Because I want to really give us quite a solid shove towards quantum field theory thought of in signal analysis way. Yep, go on.
So the noise, I'm just trying to understand better. So you're taking classical noise and you're decomposing it into its invariant and non-Lorentz noise?
Classical thermal noise has no Lorentz invariant component. Yeah. Yes. So it's just a different kind of noise, and so you can decompose. If you've got a noise, you can say, well, what component of that is Lorentz? Is not. And so you'll be able to separate them out simply because they'll have different symmetry, they'll have different invariance properties. Yeah. So ordinary classical mechanics has no such idea as Planck's constant and Lorentz invariant noise. So we're adding that in because I think we have to match what quantum field theory does. Right? So I'm following quantum field theory. What you find in the literature is people have noticed this kind of structure before, of course. But I think every one of them says, oh, look, here's the same structure. And they replace KT by H bar and say, look, quantum mechanics, without thinking about what that means. Right? So in many ways, if that's the only thing that's new that I've done, then that's what I've done as far as I can see.
You are injecting that in.
I'm injecting that into classical mechanics because that is there in quantum field theory. And we're not ending up with exactly the same structure as quantum field theory because we have this, the Hamiltonian is different, or sorry, the evolution is different. And as I say, having only positive frequency components is really hugely different from having both. But it's something we're used to from signal analysis already. But we don't equate negative frequencies with negative energy in the classical case. Yeah? So, yeah. Go on.
I just want to know if you could explain a little bit more the last thing on your previous slide about the difference in initial conditions. I think it wasn't clear to me what wave conditions are right in the complicated quantum mechanics that you're now bringing in here.
Right. So I guess this is what's the word for it? When you want to know a quantum state, you can't just do one experiment to find out the quantum state. You need to do many different things and then put all that information together. What do we call it when we constructing that way? The words have evaded me. So you have to do many such equations in order to construct a quantum state. And this is just saying that the situation is just the same for classical mechanics. You have many different classical mechanical initial conditions, which you're going to merge together into a single structure so that you can do the same as quantum mechanics. You have a formalism that is as powerful as quantum mechanics. And what this does is it formalizes your interpolation, because now when you get a new experiment, you say, well, what basis should I be using for this new experiment? And that allows you to interpolate between the experimental results from many different experiments. Whereas it would be, if you've got many different initial conditions, you have to construct a different initial condition. That's a different approach to interpolation, right? So it's not necessarily something that's going to be useful. It's just that it's a different way of thinking about these things. At a scalar field, you'll find a decomposition in the first few chapters, perhaps, into wave number components and into raising and lowering operators, where phi out of x is not a measurement operator, it's an operator value distribution, but we can construct a measurement operator by smearing, as it's called, with a test function f of x and an operator value distribution. And I'm going to call this an f measurement. The test function tells you much about the measurement. And if you look in the mathematics literature, you'll find it called a test function or a smearing function sometimes. If you look in the signal analysis literature, you'll find the same idea is called a window function. In some sense, it just describes what window you're looking at the data through. So f of x tells us where, how big, what shape the f measurement is. Now, because of the linear construction of the f measurement, we can write it as two components of raising and lowering operators. And the complex conjugate here is there for the same reason as minus sign is here. So that this is a complex linear construction. Now, just stepping back to quantum mechanics for a moment, we had measurement operators, M1, M2, and so on, but that makes no contact with the experiment. You need as well a separate list that tells you how to do each of those experiments in a particular context. So we have two lists, and we can merge those two together to give us just a single list indexed by the descriptions instead of indexed by 1 through n. And we do that because that's precisely what quantum field theory does. Quantum field theory says we'll have these descriptions, the test functions, and we can construct many measurement operators, and now the functions are effectively formal, idealized descriptions of how measurements not point like on Minkowski space. And what we have now is that quantum field theory, from this perspective, which is very different, you'll find in almost any quantum field theory textbook, but not all, is the same as quantum mechanics, except that we now have For each measurement, we've got this idealized description of what the measurement does, how it does it, whatever we think that we want to use for the measurement description, in particular on Minkowski space. So now for the free quantized Klein-Gordon field, with the F measurement can be written as two raising and lowering components, then of course we want to know about the commutation relation for the raising and lowering operators. And because of the linear construction, this is a scalar and it's a pre and a product, it's positive semi-definite. And that's on the window function space. So whenever you get two windows, you're asking, what is the overlap between them? How is the one measurement related to the other? And I show you in a few slides' time a particular specific examples of that, but we can calculate probabilities without knowing what the inner product actually is, because we just need these four equations. Then we can use a Baker-Campbell-Hausdorff identity, for example, to, well, exactly that, to construct for this expression, this Gaussian expression. Then if that test function is real valued, we can derive the F measurement probability distribution, which is normal probability distribution, with the variances given by the overlap of F with itself. So now we can modulate those states, that vacuum state, to give us modulated probability distributions, such as this. And that gives us a usefully smaller Hilbert space than the full Fock space, which the full Fock space is effectively using an infinite collection of test functions everywhere on phase space and in all possible orientations and so on. Now, quantum optics is indeed, from this perspective, is just a field theory for which we just use a few different window functions, half a dozen or a few thousand or whatever, depending on the complexity of our experiment. I find it very helpful to think of the vacuum state of a quantum field as a carrier signal for probabilistic modulations of measurements results, where it's broadband because every wave number on the forward mass shell contributes to that carrier signal. It's not like a radio signal that you're using to transmit music, because that's just a single frequency. It's also noisy because we have no information about the relative phases of each of those different components. Nonetheless, we have enough information because of the algebraic structure we've imposed to be able to construct a normal distribution for the free field and the vacuum state, just as we did on the previous slide. But we can do something to that. We can modulate that state using a coherent modulation with a G measurement now to modulate that. So now we have two test functions, f and g, that are oriented with respect to each other in one way or another. And depending on what the overlap is between those two test functions, so the overlap will be more or less, and so the displacement will be more or less in different parts of space and time. So this is just like an ordinary classical field, except there's noise as well. But we can do more than that because this is a probabilistic formalism. We can also modulate the probability distributions wholesale. We can use this construction to construct this two-hump probability distribution, or as many humps as we like, and we can vary the height of them, et cetera, et cetera. It's all Hermite polynomials when it comes to it. And where the overlap between f and g is large, so we will find it will look more like the two-hump modulation. Where it's small, it will be just the vacuum state. So the amount of the modulation will depend on the overlap. So we have the geometric structure of a free quantum field is determined by the complex conjugate and the pre-inner product. And that tells us how a modulation changes measurement results in different parts of space and time. It also, loosely, we can think of it as transmit and receive antennas. If you're going to think in really engineering sort of way, then that's a way to think of it. And it also tells us what transmissions the carrier signal supports, because not all frequencies not all wave numbers are contained in the carrier signal. It's broadband, but it's not all wave numbers. So that conditions what transmissions are possible. Now, not only can we modulate the probability distributions of a single measurement, we can modulate the joint probability distributions too. And indeed, that's what we do when we engineer coincident events in many different devices. You're engineering that there will be correlations between the internal degrees of freedom of those things, which may be hundreds or thousands of meters apart. And if you can do that, then you can describe it with this construction. If you can't do it, then you don't need this construction. But we can, of course, and so we can describe it with this kind of formalism. And I'm going to call this a Wigner characteristic function because it's only if these measurement operators all commute with each other that an inverse Fourier transform will give you a joint probability distribution, but then it will. So the reason I wanted to introduce the Wigner characteristic function is because it gives us a very effective presentation of the algebraic structure. For the free field, for the Gaussian's case, we can just use the Baker-Campbell-Hausdorff identity again to derive that there's a Gaussian noise term together with the non-commutativity term under the exponential as well. And that fixes the non-commutativity of a free field completely. This is effectively the Wick expansion in a generating function form. Now, we also want to fix the geometric and dynamical structure. We can do that in multiple ways. Just put two ways here, the two standard ways, so to speak. For the Klein-Gordon, this is a pre-inner product for which we project to the forward mass shell, and we take the product of the wave number components of f and g. For quantum optics, we project to the forward light cone, and we construct two 4 vectors, both of which are orthogonal to the wave number. Because they're both orthogonal to the wave number, this also is a pre-inner product. Now, I'm not sure whether that's immediately obvious, but still, that is the case. It is a pre-inner product. And this can be derived from, there's actually a paper that does it, so to speak, from quite a few years ago. Both of these constructions are positive frequency, and they're Lorentzian translation invariants, which of course they both have to be. In fact, they're manifestly Lorentzian translation invariant, which is a way to sidestep away from having representations of the Lorentz group. But in signal analysis, again, negative frequencies are not associated with negative energy or instability. They're not associated with something like backward causality even. They're just, do you want to work with the real signal or do you want to work with the analytic signal? It's straightforward from a point of view of signal analysis that that's okay. So remove this theta k0, which is what ensures that it's positive frequency only, this non-commutativity term disappears completely. You're left with a completely classical, completely commutative structure. But here we have a Lorentzian translation invariant h-bar scale noise. This is harking back to what I showed you earlier for the CM+. So I want to show you for quantum and quantum non-demolition optics how this works out in a little bit more detail, but not hugely. So we have the Gaussian state of quantum optics. We have the same pre-inner product we had on the previous slide. We have these set of 4 equations, and from that we can derive that indeed the commutation relation between the f measurement and g measurement is non-trivial when f and g are at time-like separation. But for quantum optics, we can find an involution, what I'm going to call the bullet involution, for which this expression is satisfied. And because that expression is satisfied, we can construct what I call an FQ&D measurement, where we have the complex conjugate and the bullet involution are in the opposite order than they would be if you were looking at the F-bullet measurement. Consequently, we have that an FQ&D measurement will commute with any other Q&D measurement. Wherever they are in space and time, this is a completely classical looking field theory. There's noise in there just the same. But it's an isomorphic Hilbert space to what we were working with before, because we're using exactly the same raising operators, and we're using exactly the same vacuum vector. Now I can show you what the bullet involution looks like for a particular case. It's not unique, by using the Hodge dual to construct the positive and negative holistic components of the test function. And then using a minus sign here. This construction does the job. It's Lorentz invariant, but it's not translation invariant, nor is it local. So this is hiding away a good deal of bad things that are going to exercise people a great deal, I think. But nonetheless, quantum optics and Q&D optics are separately, each independently, Lorentz invariant and translation invariant. It's only the relationship between them that is not translation invariant, but it is Lorentz invariant. So of course we have the quantum field theory and quantum non-demolition field theory have different algebras generated by them. However, the Q&D measurement is effectively a classical field. So we'll need to add something to that to make it possible to talk about transformation algebras and so on. Mechanics. It's called the Pales bracket when you do it relativistically, but it's effectively the Poisson bracket. We allow ourselves to use that in an unrestricted way, just as we did before. Then anything we can model with quantum optics, we can also model with Q&D optics. And of course, that's because QNDFT is just inside QFT. So it can just use the resources that are available to it in quantum field theory, if it's needed. If we don't need it, then we don't need to. We can just think classically, perhaps. So now I've been talking glibly about signal analysis as if it includes probability. But of course, if we add probability to signal analysis, we obtain something which is usually called stochastic process, which is just an indexed set of random variables. If we add to stochastic processes 1 plus 3 dimensions, and we add quantum noise, and we add generalized probability and an algebraic formalism, then we get quantum non-demolition field theory. All of the literature that discusses, and there's been lots of it the last 10 years, of course, about stochastic processes, omits this aspect of algebraic generalized probability. As a consequence, they wave their hands as to just what the relationship is between quantum field theory and their stochastic ideas. This gives you the mathematics to actually do it formally and for it to be absolutely solid, I think, certainly in the hands of a better mathematician than me. So this construction is rather like de Broglie-Bohm. We've ended up with a classical field theory for quantum field theory. But this construction is linear instead of the bilinear construction for de Broglie-Bohm. It's Lorentz invariant, which is different from de Broglie-Bohm also. And it's more measurement theoretic. We're retaining the Hilbert space structure as a tool, just as we have it in quantum field theory. So these are 3 reasons to prefer this to de Broglie-Bohm, I think. But I also want to emphasize this is not like superdeterminism, partly because it's generalized probability. But it's much more importantly, not the same as superdeterminism, because at whatever scale you're measuring, there is always going to be noise bubbling up from below. So you can never predict with certainty what's going to be happening in the future. You're always going to have noise, making it so that you can predict probabilities for what's going to happen in the future, but you can't predict with certainty. So because we're thinking more classically now, we can think of measurement outcomes as a generalized form of thermodynamic transitions, where we don't just have thermal noise affecting the development, the thermodynamic development, we also have quantum noise in there. So that will change the dynamics. And indeed, such transitions are about correlation dynamics. You're trying to engineer the correlations within the devices that you're using at large separation. And you can do that. We know we can do that because we can ensure that there are coincident events, and indeed at large space-like separation. So there's a particular case where quantum non-demolition field theory really is the natural thing to do, and that is when you're doing signal analysis. Ordinarily, we would use many measurement operators, all of which do not commute with each other. So there has to be a measurement collapse between every single measurement. So you do measurement collapse, hundreds of thousands of collapses, hundreds of thousands of changes of state. But the whole purpose of that collapse is to construct positive operated valued measures, I suggest, which allow you to construct a joint probability distribution, because these U1 through UN are actual data values. You have to have a model for that. So you construct unexpected relative frequencies to model the actual relative frequencies for those joint measurements. But of course, we can use quantum non-demolition field theory, just a lot of commutative operators instead, really just do signal analysis, frankly. And that will give us the same probability distribution, so long as we have as input to this a different state, a different Hilbert space, in fact. And indeed, that's the content of the Naimark dilation theorem, is to map from here to here by introducing a larger Hilbert space. You can introduce, we can have this instead. And we can go the other way by saying, well, we're going to encode many different experiments into a single structure. And so we can use the quantum field theory kind of description, because sometimes that's going to be better because the analytic structure will be mathematically helpful. So a prelude to interacting fields. So the Wigner characteristic function fixes the algebraic structure. And this is a generating functional form of what's called the Wightman functions, which for a Wightman field within the Wightman axioms, the context of Wightman axioms, allows you to reconstruct a Hilbert space. So what we want to do when we're constructing an interacting field is just to say what the deformation of that functional is for the interacting field. And that's what I'm now going to talk about. But first, I'm going to talk about the Wightman axioms for a moment, where they're remarkably simple. It always seemed to me. And yet there are no known well-defined interacting models in 1 plus 3 dimensions after 60 years and more. It seems to me natural to talk about weakening the Whiteman axioms to try to construct an actual model for interacting field theory. Or we could introduce completely different axioms, but that's not what we're going to do today. So we have a Hilbert space, unit reaction of the Poincare group, there's a vacuum vector, quantum fields and measurement operator value distributions. This is all exactly the same as you see in the quantum field theory sort of textbooks, one way or another. But this is a linear, results in it being a linear map from the test function space to the F measurements. Then we have measurements also support a unit reaction of the Poincare group, this time an adjoint action. We have microcausality, of course. Then we have completeness, which is just that the action of the F measurements acting on the vacuum vector generates all of the Hilbert space. There aren't any other vectors. I'm not going to talk about time slice axiom. So we've seen that quantum non-demolition field theory, signal analysis sort of feeling, will say, well, why should we deny using negative frequencies? This is a perfectly reasonable thing to do. So you've got a different kind of axioms that have negative frequencies too, and also allows non-commutativity at all separations. But what I really want to talk about, always want to talk about, is renormalization and how that really suggests quite strongly we should allow quantum fields to be nonlinear maps into the star algebra. So this map becomes nonlinear. So I'll point out first, there are two linearities implicit in the Whiteman axioms. There's one which is that states are linear, so we have von Neumann linearity, and that is needed to ensure a probability interpretation. I don't want to mess with that at all. But I do want to mess with the idea that an F measurement must be, axiomatically must be linear in the test functions. So, and that's ensured by the construction in terms of the operator value distribution and this linear construction. So we have this linearity as well. And I'm going to deny that. And I think even from an elementary point perspective, signal analysis would say, well, I've got these two test functions, F and G, and I'm going to think of those as window functions, or modulation functions. And we don't expect the response to be linear. Only to first order would it be linear, we would expect. So linearity of the field is just not so obvious in that case that it should be axiomatic. We're saying we have to have linearity there? Oh, maybe. We can use the Whiteman axioms in its linear form. Sure, we can do mathematics with that. But there's also the nonlinear form, which is signal analysis really suggests we should introduce. I don't think this is a strong argument because we might want to say that a fundamental field should be linear. But if we look at real space renormalization, we find nonlinearity is there in spades. Because if we suppose this test function, f of x, is a smearing function that's non-zero only on this square region, and we split that into 9 separate parts, then we do each of those 9 measurements, decide whether the result is positive or negative, gives plus or minus 1. We add those together, and then we decide whether the result of that is positive or negative. That's what's called the majority rule. It's commonplace in statistical physics. This I'm going to call a fragmented F measurement. And we do that over and over again when we're doing real space renormalization. So this fragmented F measurement is nonlinear in the test functions, clearly. It's very different from the bare linearly constructed F measurement, which we would take to be inaccessible ordinarily in quantum field theory. However, this dressed fragmented F measurement is arguably still a quantum field. This is the sort of thing which we would use in effective field theory. So I think that's a slightly better argument. Now we look at the renormalization group, and this took me a lot longer to get to this point where this seems natural to me, so who knows how you'll take it. This is taken from a book by Hollowood in 2013, where he suggests that the way to think about renormalization in sort of the preface or the first chapter perhaps, is to take a function f, a measurement f, to be a function of the interaction parameters of a characteristic length scale that tells you something about the measurement, and also either mu or mu prime. And then the content of renormalization is that whether you choose mu or mu prime should make no difference to the prediction from your theory. The idea that just one single length will tell you everything you need to know about the measurement is just ridiculous. It's completely unacceptable for anyone who's detail-oriented, even as detail-oriented as I am. So we should write experimental results as functionals of the information we have. And we have a tool already available to us, which is many test functions describing the apparatus. So instead of writing it as a function of L, we write it as a functional of the many test functions we have. And we should think of those test functions as a complete description of an experimental apparatus. If it's not complete, we should be adding more structure to those functions. And indeed, once we enter those into design software in 50 years' time, we should expect it to tell us whether how the experiment will work out, tell us whether the bridge will fall down or not, which after all, we have design software which will tell us that now. We also have the cutoff scale should also be dependent, is clearly going to be dependent on details too. So instead of putting your finger in the air and saying, choose a number bigger than L, we're instead going to say, we are going to be absolutely explicit. When the test functions are this is the cutoff we're going to use. So now we have that this f is a functional just of those test functions. We're going to absorb all that into this super functional f. And that, of course, is now more nonlinear than we had at the beginning. Renormalization becomes the almost trivial statement that f prime equals f when we choose different cutoff functional. So it's a more complicated argument, and perhaps it's not completely compelling, but altogether I find this compelling, of course. So if you say, well, we're going to accept this, we're going to say that an f measurement is nonlinear in the test function, we can now take a functional derivative of that. Double functional derivative will give us a 2-point operator value distribution. This is far beyond anything that's in the Whiteman axioms. Just introducing nonlinearity has introduced something which is just completely different. And yet this is something that has been used by a few authors, Wayne Polizu in particular. They've used this kind of structure to model bound states, which are problematic in quantum field theory. That's why they wanted to use such a structure. Now, this is a mathematical nicety, this next point. I don't really have time to go through it, but if the f measurement is not expressible as a functional Taylor series, which will be the case if you just have than, so a cutoff applied to the test function, then there'll be singular points in the complex plane, which the test functions will have to avoid. And potentially, it seems to me this is going to result in discrete structure, at least a different kind of discrete structure than you'll find in any of the existing formalisms for quantum field theory, it seems to me. So there's actually a sort of hint of this kind of structure appearing in a recent article in concerning curved space-time, where there's a complicated argument that the space of rescale correlators is similar to that of n-variant distributions. And that becomes a surjective map if we work with flat space-time. I mean, I'm all flat space-time because the curve stuff just is way too complicated and obscures a lot, it seems to me. But given the reasoning on the previous slides, I suggest we should just use nonlinearity. And if we can manage with just multilinearity, then fine. But introduce nonlinearity in the first instance. So I've argued that renormalization suggests nonlinearity. I'm now going to argue that actually it's enough. Because if you look at a conventional Lagrangian deformation, sort of chapter 3 or 4, you'll find an expression such as this for constructing a generating functional. And this J is called a source typically, but it's just a test function. And if you insist on it being Lorentz invariant, then of course it's not well defined. But we're working here with the Whiteman field. And so we have available to us the Riesz-Leiter theorem. Now, the Riesz-Leiter theorem is a weird beast that a lot of people are not happy with, but the mathematical content is that local operators acting on the vacuum vector, V, can approximate any vector that you can construct using operators anywhere in space and time. It's an analytic property of the Whiteman axioms that allows you to do things locally that you'd think could only be done globally. But if now we introduce any regularization that lets this vector, so a regularized form of the ZJ operator acting on the vacuum vector, if that's a finite norm, we can approximate that vector. And it's going to be a nonlinear functional, inevitably, of the test function J. And we're going to construct it using only nonlinear local functionals of J. Now, renormalization inevitably makes this more complicated, but we can think of it as just introducing mass and length rescaling. And that we can accommodate by using a collection of different fields. So we have M kappa. So each F kappa has a corresponding M kappa for different functionals. So now we're well used to modeling the physics with this vector, or the vacuum expectation value version of it, and then using functional derivatives to construct, say, a 4-point vacuum expectation value, which I've smeared in this case with 4 test functions, so I can display it like this. When we could have this construction for this particular one, we integrate the variables y1 through y10 over all of space and time. Of course, that's problematic unless we do a regularization and renormalization. On the other hand, we've just seen that we can, I've thrown at you the idea that we might be able to, a good mathematician might actually be able to prove it, that we can use nonlinear overlaps between f kappa applied to fi and f kappa applied to fj with the kappa in language. So here we're going to apply f1, the functional f1 to the test function f2 and the functional f1 to the functional f4. That's going to give us a pre and a product. And then we're going to have lots and lots of sums and products of that. And we know that we can do this because that's what the Richelieu theorem says we can do. It says we can have a local construction of what we have been constructing with path integrals. Not a simple thing to do, but nonetheless, in principle, it can be done. And this is going to work out much more straightforward in its way. So the interplay here between local and global is rather similar to what you find in holography, because this is entirely about the analytic properties of the Whiteman axioms, making this possible. So I've argued that analysis of renormalization and of path integrals say we should, and it's enough to introduce nonlinearity. So we want some manifestly Poincare invariant functional of the lambdas and the f's, and we want to present that in different ways. So this is just a functional. You can decompose it in any old way. You can choose any sort of basis for it. Some bases are going to be nice. Some bases are not. So I can't tell you which is going to be nice. If I could, then this would be a much, much better talk and also much longer. But we want something that gives us good intuitions about what's really happening inside an experiment. So this is starting to sound really pretty realist. But it's also now, it's completely well-defined. This construction is completely well-defined in a way that the path integrals are not. And of course, we might want to use mathematics that a much better mathematician than I am would say, well, you want to use the Wigner characteristic functions. Why would you want to do that? Why not use this category theoretic thing I've got over here that is much better? I don't want to prejudge what will work out best. But I can say to you there are two tentative constructions which work perfectly well as a first stab. And that is, to begin with, we can just construct a nonlinear Gaussian field, which then we want to construct something non-Gaussian, for which there's two measurement vacuum expectation value is nonlinear. So we have the linear thing here, and we add to it a nonlinear construction. And this fairly straightforwardly can be shown to satisfy the requirements for it. So that just gives us a sum of many binary relationships instead of path integrals. But then we can follow a slightly different path and follow the ideas we have from the phi-4 theory, for example, where you can construct an integral equation equivalent to the phi-4 theorem. And this follows that structure. And if you use this kind of construction, then this gives us a recursive cloud of measurement operators. So you start off with the test function f, and then you consider all the fragments within it, and fragments within it, and within it, and within it. So it gives you a fractal kind of structure, although you can stop at any point and you'll still be satisfying microcausality. And this integrates over different fragments, over the kappa variable, instead of integrating over all points everywhere in space and time. Okay, this I don't have time for. I didn't set my timer started, but we have for this is a concise list of the difficulties of quantum field theory. I'm not going to talk about all of them because of time. But the idea that there are no particles in quantum field theory is something that has occupied philosophers and physicists quite a lot in the last 20 or 30 years. But by weakening the axioms, we've introduced the possibility of there being more models. And in particular, we've introduced nonlinearity. So now we have nonlinearity and dispersion, which if this was a classical field theory would be enough to say, well, we're going to be having solitons here. And certainly we're going to be having caustics. If this isn't enough, then we should weaken the axioms more. But I think the first thing is to say, well, let's just do that and see what the consequences are. So how can we use this towards quantum gravity? I've argued that we should be thinking in terms of just a few different measurements. So just description 1 through description n, not all possible test functions and so on. Then all we need for us to be able to construct a Gaussian state and to work with probability distributions for a particular experiment is one positive semi-definite n by n overlap matrix, which tells us the relationship between each of the descriptions. So that gives you an n by n matrix. And if that was a linear construction, this would be called a gram matrix. For a nonlinear construction, the computer scientists and mathematicians would call this a kernel. So suppose we managed to construct a successfully deformed optics. Next year, possibly not. Time, who knows, which combines many kernels, so indexed by kappa, in such a way that rho v prime is still a state. It's actually straightforward to do, but whether to do it and actually have a physical model is another question. So suppose we have, let's not say that again. For quantum gravity, we can introduce a new description, which takes the bivector test function we first thought of, but now we add as well a background we want to impose. Now, this is completely different from anything you'll see. We're not saying that's how the background is. We're saying this is a background we want to apply as a modulation to the vacuum state, to the quantum gravity vacuum. So we're not making any claims at all about what the background actually is, about what is actually underlying. This is much more empiricist than that. Nonetheless, if we have this construction, we have the kernel, wherever the kernel FIFJ with the kappa index occurs in this successful deformed optics, we replace that by a new kernel. That will give us a candidate optics that in fact that is a quantum gravity. It's a candidate, so the first one you think of is not going to be the right one, but it is actually going to give you results at all possible scales. This is not going to be a renormalizable sort of situation at all. This gives us a measurement theoretic approach to gravity that's different from anything, I think. This is not about quantizing gravity. It's not about gravitizing quantum or about gravitons at all. There's no discrete structure in here necessarily. You can have discrete structure by just making things right. There's no claims as to whether this is about lattices. It's a model-independent sort of approach, precisely because it's so empiricist. So now we have, I think we can have a stab at a very minimal axiom set for quantum or quantum non-demolition gravity. We say, well, we have n measurement operators that are nonlinear in the measurement descriptions. And then we say, well, we'd like a manifestly diffeomorphism invariant state for that. And that will allow us to use the GNS construction of the Hilbert space. Now, the next step is, do we or do we not encode causal structure into the algebraic structure? If we choose to do so, then we're effectively choosing something like the spectrum condition of microcausality. On the other hand, we can back away from that and just say, well, let's have just the classical quantum non-demolition case. And when we understand causality better, then we can see whether we can actually do quantum gravity or whether we should just work with quantum non-demolition gravity. And I think it seems to me that the 3B is an easier playground. Nonetheless, 3A may well be the one we want to have in the end, because it will have the analytic structure, which will be helpful to us in the mathematical sort of way. So now this is a throwaway line, really, again, about large language models. It seems to me that invariance should be about more than diffeomorphisms now. Because if you have a large language model, it's extracting information about a measurement, about an experiment. From a journal article, there's one in Chinese and one in English and one in French by different authors about the same experiment. You want to extract all that information that I say to someone over a drink in a pub, maybe in that document, but can't be expressed in terms of test functions. That information nonetheless should be grist to the mill for predicting what the results of an experiment will be. Yeah, if anyone has to leave, then obviously I'm very close. Well, perhaps not obviously, because it's not showing the bottom. We actually, this is the last slide. So I've argued that we should talk in terms of actually recorded measurement results. And that's something very close to Copenhagen, except that we've focused on data sets instead of on particle properties. This really is completely different. Focus on data analysis and statistics of actual data and the prediction of that and expected statistics. I've argued that metadata is vital, that it really changes the game if you think in a computing kind of way where you want to know what the README file is for your data. If you haven't got the README file, if you don't know what the encryption is, then there's not much you can do with just an arbitrary number of terabytes. And I also said that we should allow ourselves to think in terms of classical measurement incompatibility. So if we allow ourselves non-commutativity in a classical context and quantum noise, that gives us a structure that allows us to talk about an experimental apparatus here, either using quantum mechanics or using classical mechanics, CM+. Now this experiment is not quantum or classical. It's just an experiment. It does not care whether I, in my head, am thinking about it in terms of quantum mechanics or in terms of CM+. It really changes the game as far as quantum computing is concerned, because you're just constructing hardware that's good for a particular algorithm. So I think there's no such thing as non-classicality if we allow CM+. For CM+, as I argued before, measurement events become just much more like thermodynamic transitions, so the measurement problem is kind of dissolved. It's not exactly going to be simple, because there are two types of noise now. Nonetheless, the idea of quantum is not vacuous at all. It just means that quantum noise, the Lorentz invariant noise, can't be ignored. So I'll skip this because it's just saying what I've just said. My reading of the literature of the last 20 or 30 years is that quantum and classical have been converging in many different ways. This talk is my attempt to push that forward a little bit, or perhaps and hopefully give some indication as to how I think it will be in 5 or 10 years' time. Nonetheless, this is something where there are no CM+ textbooks. If you want to do quantum optics, you are absolutely not going to want to do this next week. You, on the other hand, have this in the back of your heads now, insofar as I've explained it all. Well, from here we go. Thank you for your attention. So I did say to people earlier that I have been recording this, including the fiasco in the middle. If anyone wants to be edited out at the end, then just say. Otherwise, leave the room or such like. We'll see whether I can make a fool of myself, even if you can't make fools of yourselves. So, happy to answer questions.
Yeah, earlier you mentioned that think of measurement in this framework as a sort of phase transition.
Right.
Does this display any similarity to the measurement-induced phase transitions we see in random circuits?
Don't know. Don't know anything about random circuits.
Okay, this is speculation, but like vibes-wise, based on like the equations you showed,
yes,
I think there could be.
Right. I mean, manifestly, there's a whole pile. I could have 1,000 references in this, of course. I mean, and 1,000 more that I should know that don't. That is indeed random circuits. So yes, absolutely, because I mean, the stochastic electrodynamics, for instance, from the 1960s, really should be ringing bells for anyone who's ever seen that literature. The 0-point fluctuations is exactly what I'm saying for quantum noise. And well, just a slew of other things. As far as the signal analysis work is concerned, there's a guy called Anastopoulos who has a lot of work about signal analysis, but never quite gets it right. He doesn't say the story in a way that you say, oh, that's what this is all about. Frankly, I see that and I think to myself, I'm sure I'm also doing the same. I think I'm being absolutely clear and everybody else is saying, okay, maybe, but really I'm not explaining it well enough. The mathematics, though, is simple enough and explicit enough in this that it seems to me that someone else at least can do the mathematics better than I can and produce something that, well, will be a CM+ book or whatever in 5 to 10 years' time. Would be nice to see. Do a Dirac on it, should we say. So, any other really vague question that I can really sort of wander around about?
Very basic,
Sam.
maybe you can talk offline as well. You mentioned already quantum computing implications. Also putting on my
Yeah, quantum CT hat, yeah.
team hat. Any implications with respect to error correction algorithms?
All of the quantum textbooks stay exactly the same. Every quantum computing textbook is exactly what it was. I have no beef with that stuff. It's what you're doing with those textbooks is constructing a way of specifying algorithms that can be run on a quantum computer, which specifically is designed so that I think particularly the issue for me is the timings of operations in a classical computing is very much there's a system clock that everything has to go with the system clock. For a quantum computer, there's no such thing. Okay. So I think this will, in course of time, will result in some people saying, oh, this allows us to think about our quantum computer in a classical way at the hardware level. But the software level of a quantum computing programming language will be a good way to specify some kinds of algorithms. So I really don't want to, the quantum computing is still in the game because, as I say here, the quantum just means that there's a, I seem to have lost, just means there's quantum noise that can't be ignored. And one way that people do talk about quantum computing is to talk about quantum noise as a resource. Right. And this really says, yes, quantum noise is a resource. What this also suggests, though, is that you might be able to use thermal noise as a resource too. The great thing about quantum noise is that it's fixed to like 6 or 8 decimal places, whereas thermal noise, fixing the temperature to 300.00000 for any size object is difficult. Nonetheless, that is not necessarily differently harder to do than keep it at 0.00 to within a nanokelvin of 0. So it may be that we can do, and of course, when you look at things like D-Wave, it may well be that they're actually doing the thermal Hilbert space version of quantum mechanics. That's real speculation, but still, it's just sort of, it's always seemed to me that there would be scope for a thermal version of quantum computation because we have the thermal Hilbert space can be computed can be constructed. Okay. Yeah. So, and indeed, there are things like p-bits in the quantum computing, in the round quantum computing literature, and there are people doing all sorts of classical algorithms. You've got some people like Yuan Tang saying, well, we can do this classical computation, which is equivalent to this quantum computation. The complexity is the same. This says, at a deep level, well, of course, because it is just CM plus calculation. If the algorithms you're using go beyond classical mechanics into what CM plus can do, then yes, it will be classical. But this says, well, it doesn't say it's pointless doing that kind of work at all because it's good mathematics, but it does say that there's it puts it in a different context. Yeah.
I wanted to ask about, you said something about the lower bounds of CN plus.
Sorry, about the
lower bound.
Oh, the lower bound, the energy, yes.
So I should think of these like KT fluctuations as being able to be infinitely small. Is that right? Whereas like the kind of quantum vector is planned by H bar. Is that...
Now as far as the I'm going to diverge from your question. I hope that it actually will answer what you want to say. Oh, here we go. In quantum field theory, one finds that the quantum vacuum is Poincare invariant, whereas thermal noise is not. So you find if you do work out the vacuum expectation value, it's just this expression as we saw before, except this is not smeared. So you have a projection to the forward mass shell. If you work out what the thermal state is, it's exactly the same, except that the Koth hyperbolic tangent applied to h bar k0 over 2kt. So that is not Lorentz invariant. And that's a calculation you can do fairly straightforwardly. Now, both of those constructions, if you look at smaller and smaller regions, the variance, the pre-inner product of f with itself, goes to infinity as the size of the regions goes smaller. And that's because when you average them over a larger region, then of course the variance can go down because there isn't much correlation between the things that are close together. So the fluctuations get bigger and bigger and bigger in the model. Whether they really do to all possible small scales is another matter, of course, but the model says the fluctuations will get bigger and bigger and bigger. I can actually construct models in which that's not the case. But when you do, then you find it gets complicated, but you can do it. So I'm not, as I say, I'm not sure that did answer your question. It's a sideline from, so if you ask your question again in the light of what I've just said, or...
Yeah, so I mean, I guess so what are the lower bounds? Because I would say in quantum mechanics, right, it's like a discretize like energy level, for example.
Right. Everything I've done here is bosons, fermions. I don't have a solid story for, I have some story for it, but nonetheless, don't have a solid story for it. And the interactions, the story I have to tell about the interactions is far short of describing a hydrogen atom, far short. It's always seemed to me that it's only when you have a confining potential that you ever have a discrete spectrum. And a confining spectrum, a confining potential is always something where you've constructed a vacuum chamber around your atom or your 100,000 atoms and a whole elaborate electromagnetic field to keep them in the place you want them to be in order to localize them by, and that's the nonlinearities of the magnetic field acting on those atoms. So at the scale of atomic physics, of even of, well, the electron kind of dissipates instantly if you have just a single electron with nothing around it after all. So you'd have to have that surrounded too. Now you're talking about confined systems, and that confinement then, the effective model is just going to be the same as in quantum mechanics. So ordinarily, the things you learn in sort of year one of a quantum mechanics course, just the inverse potential, inverse R potential, not going to be different. I mean, I'm all for effective field theory in one way or another, but this allows you to actually say, well, that does derive from this system, which will predict, again, just as for a free field, what the measurement results would be at 10 to the minus 1,000 meters. Even in situations where you'd say, well, we'd have to do renormalization. So this is a every scale formalism. And so complexity theory is going to come in eventually because, you know, the statistics is going to be wildly complex for some forms of the dynamics. It's a different way of thinking about things, of course. I've been doing this for 20 years at least, and I don't have much of a handle on this. So if you've got any handle on this after an hour of this, then you're doing very well. Okay. Anyone else? So I'm just going to stand here until everyone's left. Thank you, guys.